Chapter 3 is a little bit different than Chapter 2 because Chapter 3 is mainly conceptual. So, very little math compared to Chapter 2. Our aim for the first section, 3.1, is to learn about matter and its three states. So, this is something we've learned about in middle school. When we initially learned about the three states of matter, we're just going to look at it a little bit more in depth in terms of what's actually happening at a molecular level. So we're going beyond just solid, liquid, and gas, and we're going to talk about particle distance, volume, shape, compressibility, and all of the aspects involved in being a state of matter with those characteristics. Looking at the three states of matter, three most common states, solid, liquid, and gas, and we're going to be looking at the different properties that make up those shapes and how we can differentiate between one state of matter and another. So looking at a solid, first of all, the volume of a solid is what we would call fixed. That volume doesn't change. It's either in cubic centimeters or milliliters if we want to be able to convert, but that doesn't change. That is calculated by looking at length times width times height. So you have three dimensions here, and we looked at calculating the volume of a rectangular prism when we were doing the density lab, and you had to look at the three different dimensions, length, width, and height. So remember, we calculated this value in cubic centimeters. So remember, a cubic centimeter is equal to a milliliter. That's how we're able to go back and forth between volume when referring to solids versus liquids. If we're looking at the shape of a solid, that is also fixed. So this is an object that we can place in a container and it won't change. It doesn't morph into another shape. Whatever object this is, a rectangular prism of sorts, will hold its shape if we put it in a container. So would a cylinder type object, like we saw in your density lab. If we're looking at this at a molecular level, we're talking about particle distance. So we know that in a solid, the particles are as close together as possible. They're essentially fixed in position. They do still have a little bit of motion, but they're not moving enough to form another shape. That's also why we say the shape is fixed. Now, compressibility refers to whether or not we can push these particles any closer together. So if we're saying in terms of particle distance that the particles are as close together as possible, then we can also say that a solid is incompressible. We cannot push those particles closer together because they're already as close together as they can be. There's no empty space between these particles. So picture this like chalk dust inside a syringe. Chalk is a solid, and even though the particles are very fine, there's not enough air in between them to be able to depress that plunger and push those particles any closer together. They're already as close together as they could be. As far as types of motion, they're as close together as they can be, so we don't have any movement of those particles, we don't have any rotation of those particles, but we do have what's called vibrational motion. So every object has vibrational motion just by virtue of its existence. This looks like a bending or a stretching of the bonds in between the particles, and that's about all we get out of the motion of a solid atom or a solid molecule. Most people, when referring to states of matter, like to use examples of solid and liquid and gas, like ice, water, and steam. So remember, the solid sample of matter would be the ice cube. Remember, it holds its shape and it's got a fixed volume. You can't push those particles any closer together. It's incompressible. And at a molecular level, all they can do is bend and stretch. Liquid would be liquid water. Volume of liquid water is fixed. So we are able to actually pour that sample of water into a graduated cylinder and we can measure what that volume is. So remember, we're talking about milliliters here. That's equivalent to cubic centimeters, but remember, we're not taking the measurement of the three different sides of a sample of water. We're pouring it into a container that does the measuring for us. In terms of shape, liquid takes the shape of its container. So you can see when you put liquid into a container, it's going to form either cylindrical shape if you're putting it in a glass. If you're putting it in some kind of a rectangular prism shape, it's going to form the shape of that rectangular prism. Takes the shape of whatever container you're putting it in, so it molds to that container. Particle distance, relatively close together. Not as close together as in a solid. They have a little bit more freedom of motion, which we'll get to in a minute. Those particles are still close together though. So we can see they have a little bit more space in between them, but in terms of compressibility, they're still considered incompressible. There's not enough space between them, not enough empty space that we can consider that sample to be compressible. So we cannot put this in a plunger and push those particles any closer together. If you've put water in a plunger and tried to depress that plunger, the water cannot get any smaller in terms of its volume. Those particles cannot move any closer together. So we still have vibrational motion here. Remember, everything has vibrational motion. But now, since water can flow, we've developed this rotational motion. So the particles can start moving around each other. So we can have a bend, we can have a stretch, and we can have a turning motion. So they have a little bit more freedom in terms of their movement, but they're still not able to completely move away from each other. They have to still stay in the same neighborhood as their neighbor molecules. And the last state of matter would be gas. So we have a solid, which would be the ice cube. We have liquid, which would be liquid water. And then we have a gas, which would be steam or water vapor. So if we think about the volume of water vapor, we don't have any measurable volume in terms of water vapor. Water vapor would completely expand if we tried to place that in a container. So it, for that moment, would take the volume of that container. But as soon as we put it in another container, then it would take the volume of that container as well. So the volume in a sample of gaseous matter is non-existent. The shape, we say that it fills the container. It doesn't just take the shape of the container, it completely fills the container. We saw in liquid how just taking the shape of the container is one thing because it does have a definitive volume, but when we're talking about the shape, it expands to fill its container. So that's what makes it a little bit different. Particle distance, these are as far apart as possible. I could put this in a small container and it would expand to fill that container, moving those particles as far apart as possible. I could put it in a bigger container, and because it expands to fill its container, those particles are as far apart as they could possibly be. I could put it in the largest container I can find, and it would still expand to fill its container, which means those molecules would be as far apart as possible. So now we have a lot of distance in between these particles. And if we have a lot of distance in between the particles, that means in terms of compressibility, gases are considered highly compressible. I can get rid of that space in between those molecules. So we can picture this like if the plunger was fully open all the way to the top, and this was a gas sample, and then I decided to depress the plunger, I can get rid of the space between those molecules. And now all of a sudden I can change something in the gaseous phase to something in the liquid phase because those particles are now close enough together that there's no space in between them, similar to what I would see in a liquid. As far as types of motion, we still have vibrational because they still exist. We still have rotational because they can still rotate around their bonds. But now we have translational motion. Notice because they can expand to fill their container, they now have the ability to move. So we can bend, we can stretch, we can turn, and we can move. If you've taken geometry, you've probably seen that word translation before. And that's when you have coordinates of a shape and you change the coordinates, and that's called a translation of that shape. The shape will move along the axes. So that's what we see here. In a gas, we have all three types of motion: vibrational, translational, and rotational.